Okay, so these are the notes on predicting precipitation and common ion effect that we did in class. Um, so the first thing you're going to need to do when solving problems with solubility is write what looks kind of like a chemical reaction, but what you're really showing is the dissolution process. So you write your solid on the left side, and then um, do the arrow, the equilibrium arrow, and then show the ions that it breaks into. So we're going to compare Q to K to determine if a precipitate will form. So think of Q as those are the initial reaction conditions. So Q is the concentration of the barium, in this case, the barium ion concentration times the concentration of the sulfate ion. There's no powers because there's no coefficient in the equation. And then K is at equilibrium. So remember, if Q is greater than K, then the reaction is going to go to the left, to the reactants or to the solid side, which is the precipitate. So if Q is greater than K, then that means that the that the reaction or the dissolution is going to go in reverse. And that means that you're going to start making more of the solid, which is the precipitate. So it's going to be less soluble, which really means that you're going to have more solid that precipitates. Now, if Q is less than K, then the dissolution continues to the right. It's more soluble, and we're going to see the concentration of the ions increase. So basically more ions in solution that will be produced. If Q is equal to K, then you have equilibrium, and we have what's known as a saturated solution. Okay. All right, so when we make solutions, sometimes we don't make them in pure water, or if a reaction is taking place, there may be other ions in the solution as the reaction is happening. So we have something that's called common ion effect. So it states that the solubility of a solid is lowered if the solution already contains ions common to the solid. So think of this as trying to dissolve a compound into a pre-existing solution that already has one of the ions. If it already has one of the ions, that is called the common ion. So it's going to be more difficult to get it to dissolve, and that is because of Le Chatelier's principle. If you already have ions that are present, that means that the concentration of the ions is greater, and Q is going to be greater than K, which means that the equilibrium is going to shift to the left, which means you're going to have more solid, fewer ions. Okay, the concentration of the ions is going to be lower than what you would expect because there's already a common ion in the solution. So since there are ions that are, we might want to put in here, already present, it's going to shift that equilibrium to the left. Okay, so how does this look in solving solubility problems? If you want to know the concentration of the ions at equilibrium when you already have a common ion. Well, so it says what will be the molar solubility of silver chloride solution if the solution already contains 0.75 molar sodium chloride, and it gives us the solubility product constant of silver chloride. So I can see that this silver chloride is being dissolved into a solution that already has sodium chloride. Here is my common ion. So that's kind of what you want to look for is, okay, here's my solid, here's the solution that's being dissolved into, here's the common ion. All right, so we're going to have an initial concentration of chloride ion already in there. It's 0.75 molar because it's a 1-to-1 relationship. Every 1 mole of sodium chloride, you have 1 mole of chloride ions. So if I have 0.75 moles of sodium chloride in a liter, then I would have 0.75 moles of chloride ion in a liter. Remember, we did that back in Unit 1. So I'm going to go ahead and write my dissolution reaction for silver chloride. So I have AgCl, because I'm going to need my equilibrium expression. And that breaks down into silver ions in solution and chloride ions in solution. And what we have to remember is that we already have a molarity for our chloride ions. So I'm going to have an initial, a change, and an equilibrium. Since this is a solid, I'm just going to X that out. I don't need that. So the initial of silver is 0. The initial solution has 0 silver ions in it. But my initial solution has 0.75 molar chloride ions. For the change, I'm going to have plus X and plus X, because I'm adding in a certain molarity, but I'm going to figure out what that will be. And then at equilibrium, I'm going to have X and 0.75 plus X. Okay, remember these are in a 1-to-1 relationship, so I don't need any coefficients out in front. Okay, so my equilibrium expression is 1.8 times 10 to the negative 10th is equal to the concentration of the silver ions times the concentration of the chloride ions. Okay, so I'm trying to find these molarities, but I already have a concentration of chloride ions. So we're going to find out what that molarity is going to end up at the end of the dissolution at equilibrium. So I'm going to fill these in. I'm going to put 1.8 times 10 to the negative 10th is equal to X times, and this is kind of nice, because the equilibrium constant is so small, we can ignore this plus X on here, okay, times 0.75, okay. So on these equilibrium, these common ion effect problems, it's kind of nice. We can actually just ignore the plus X because it's going to be such a small amount that changes. All right, so I'm going to divide by 0.75. Divide by 0.75 and solve for X. So the molarity of the silver, and this would be equal to the molarity of the chloride ion, is 2.4 times 10 to the negative 10th molar. Okay. All right, so let's go down here and try another one.